This is the discussion that we've been building on for quite some time. It's the concept of modulation. Specifically, or what we're going to focus in on today, is amplitude modulation. Keep in mind that there are other types of modulation. For example, at some point in the future, we'll talk about frequency modulation. But for now, we're going to talk about amplitude modulation. Earlier, we defined voice frequency as approximately 300 to 3000 hertz. We also described the limit of human hearing as somewhere between 20, and if you're very young and haven't damaged your ears, all the way to about 20,000 hertz. We defined bandwidth as the upper frequency, so an F2 minus an F1. And that was quite easy to do when you were in the frequency domain. For example, if you had a signal with a fundamental and then some harmonics, you could describe a bandwidth like so. You could say this is the F2 and this is the F1. As we've gone through the labs, we have looked at the spectrum of people speaking, and we've also looked at the spectrum of music, which generally follows what humans can hear. With these thoughts in mind, we're going to shift to the software-defined radio and look at a few AM radio stations. One of the things I want you to ask yourself is, can you tell the difference between music and voice based only on the spectrograms? For our discussion, we're going to look at the medium wave broadcast band, which is what you know as the AM broadcast. It goes from approximately 500 kilohertz up to about 1600 kilohertz. And you can see all of the stripes here. Those are the individual stations. This one is most likely carrying music. By the way, you'll notice that we can change the filter width. Right? So we have a bandpass filter which serves as the tuner for this radio. And by adjusting the receiver, we can match the broadcast. Okay, so that one's music. Sometimes it's hard to tell. This one looks like it could be voice, but I've been wrong before.
Guy behind the bar is so socially awkward. He's the one guy you don't want. He could be.
There we go, definitely voice. You'll notice that there's symmetry on either side. That's something that's important to us as we go on. I believe I talked about this, where we talked about a lower sideband. For example, if I change the filter here, this is our center frequency, and this is the lower sideband. And this, again, this is where we're tuned. This would be the upper sideband. So AM consists of two sidebands. There is symmetry in those two sidebands for an AM broadcast. Later on, we'll talk about things that aren't symmetrical. While we're here, you also notice that there's this center carrier that's very bright. And you see that on all the stations. You see it over here, you see it here, you see it here. Okay, and that doesn't appear to change ever. Anyway, the main point in all of this is to notice that there is some relationship in this waterfall diagram to the spectrum that we looked at earlier. Right? You can see the voice in this particular station. Or if we look at something with music, you can see that there is some structure with low frequencies here and high frequencies here. Here is a sketch to illustrate what we're talking about here. So we have a speaker, a microphone, a wire leaving that microphone going to a transmitter. That transmitter has a device called a modulator. So the microphone might go through an amplifier to boost the signal, but then it goes to the modulator. The output of the modulator may or may not, depending on which type it is, go to another amplifier before it leaves the transmitter and goes to the broadcast antenna. As part of the modulator, we're going to introduce a new term called local oscillator. So again, local oscillator. We said this was an amplifier, the microphone, and the modulator, which exists inside the transmitter. Our objective is to take something like voice frequency and superimpose it on the local oscillator. We do this for a couple of reasons. First, voice frequencies don't travel over the air very well. It doesn't matter how big your amplifier would be. If you connected the microphone to an amplifier to the transmitting antenna, you're not going to be able to transmit very well. High frequencies, on the other hand, transmit extraordinarily well. Also, we have something that we're going to call baseband. And so we have these baseband frequencies, which is another word for the voice frequencies in this particular example. But anyway, it's like a crowded room, right? If you're talking and I'm talking and somebody else is talking, they all interfere with each other. And that's not particularly useful. And that's exactly what would happen if each radio station tried to transmit at the baseband voice frequencies. Instead, what we want is the ability to do what we did with that software-defined radio, and that is to move it to a particular location. And the secret to that, of course, is the local oscillator. Here's another way to look at this. Let's start with our voice frequencies. So in the frequency domain, I'm going to sketch this as a wedge. And we'll let that wedge of frequencies go from 300 hertz to 3000 hertz. And we said that voice frequencies do not transmit very well. Very difficult to do. However, if you amplitude modulate, if you run these frequencies through an amplitude modulation, so AM, you end up with something that's quite different. In the frequency domain, a carrier is introduced, and then that wedge of frequencies ends up here in the upper sideband, and it's duplicated here in the lower sideband. The upper sideband and the lower sideband are symmetrical. So this is the carrier, this is the upper sideband, and the lower sideband. As far as frequencies are concerned, if we let the carrier be 1 megahertz, the lower limit of the upper sideband becomes 1.003 megahertz. That's not right. We missed a 0 in there, didn't we? Let's try that again. 1.0003 megahertz. And the upper limit of the upper sideband becomes 1.003 megahertz. The lower sideband starts at 0.9997 megahertz and extends all the way down to 0.997 megahertz. LSB stands for lower sideband and USB for upper sideband. And as you can see by the way they've been drawn here, they are mirror images of each other. One of the questions that you'll certainly be asked is, what is the bandwidth of the AM broadcast? That's not so hard. This is our F2, this is our F1. So the bandwidth is equal to 1.003 megahertz minus 0.997. which means our bandwidth is equal to 6 kilohertz, which just happens to be 2 times what our maximum baseband signal was. Let's take a look at this concept from yet another angle. Remember, last time we met, we talked about the Fourier theory, where we said that a periodic signal could be composed of the sum of sinusoids. If we consider a person speaking in the frequency domain, we've sketched that as a wedge of frequencies. Inside this wedge, there are going to be fundamentals and harmonics. In lab, we looked at the word my, and it definitely had lots of energy in the lower part, and then there was harmonics riding on top of it. What Fourier allows us to do is to disregard all of this complexity, all of this harmonics, and take the signal apart and only focus on the highest frequency. Here, we define the highest frequency to be 3000 Hertz. When it comes to our modulation, we can look at one tone in the frequency domain. In this particular case, we pick the highest tone, so that's 3K, and that's the only one we really worry about. Now, this AM modulator has a local oscillator associated with it. We'll let that be in the frequency domain 1 megahertz. Our output in the frequency domain will consist of a 1 megahertz carrier, which of course is the local oscillator frequency, and then we'll have a spike on either side. So the upper sideband, again this is in the frequency domain, would be 1.003 megahertz, and the spike as the lower sideband would be 0.997 megahertz. Let's go ahead and add some terms which will make this a little bit easier for us to talk about. This is the carrier, so we talk about the frequency of the carrier, and this is the frequency of the modulating signal. In tabular form, we would talk about the frequency that is used to modulate. We would call this the baseband intelligence. In this example, that's a voice frequency, but it doesn't have to be voice. It could be a signal from a computer, like a modem. As a side note, do not confuse this with FM. If we're going to talk about frequency modulation, we will write it this way, capital F, capital M. This is F sub M, where we're talking about the baseband intelligence. So if we went back here, the baseband intelligence would be this, F sub M. It's the information that you want to send over the air from the transmitter. The frequency of the carrier. And carrier is a pretty good word because it is the carrier frequency, this FC, that's used to carry the intelligence. By the way, this is FC plus FM. This is FC minus FM. So transmitter outputs for AM, we have a steady carrier. We have the upper sideband, and that occurs at the frequency of the carrier plus the modulating frequency and the lower sideband. And that occurs at FC minus F sub M. The bandwidth of our AM modulator, B, is the frequency of the upper sideband minus the frequency of the lower sideband. Or if you prefer, bandwidth is simply 2 by the frequency of modulation. Do make a note here This is the highest frequency to be transmitted. For example, in the frequency domain, music might extend from 20 hertz all the way up to 20 kilohertz. If we were to send this as a broadcast, right, you would have all of this energy, all the way from 20 to 20K. The bandwidth of our AM transmitter would be 40 kilohertz, which is fine in some applications, but not all applications. Because remember, in the frequency domain, we have allotted space for each channel. Right? If this is the music channel number 1 that you like to listen to, and this is the voice channel number 2, and this is yet another radio station you'd like to listen to, each one must live within a certain bound. Because if number 2 is not playing nice and the bandwidth extends past these ranges, what will happen is it will interfere. So number 2 and number 1 will collide here, and number 2 and number 3 will collide here, which makes for some very unpleasant noises. What we do to prevent that is use a filter. We take the output of the microphone and we run it through a filter. Typically a band pass filter. In fact, you could call this the voice filter, with a band pass of 300 to 3000 hertz. And from there, you can send it to the modulator, complete with the local oscillator, to the amplifier if necessary, and then to the broadcast antenna. Here, this voice filter determines the bandwidth. In this case, bandwidth is going to be 2 by 3000. So our bandwidth is 6 kilohertz. If we go back to our software-defined radio, we are listening to the BBC Radio 5 at 693. Now that 693 kilohertz is the carrier frequency, right? That is the carrier, this bright band in the middle. The bandwidth of this particular station, you can see, is this frequency minus this frequency. And just so we can get our bearings here, this is the number 702, this is the number 684 kilohertz. The difference, which is here to here, is 18 kilohertz. And now we can look at this filter, which is currently set to 12 kilohertz. We could narrow it if we like, which isn't going to leave a very good sound because all of the upper harmonics are gone from the voice, or we can make it much wider so that it matches the transmitted signal. If we work our bandwidth frequency backwards, right, that's the frequency that tells us bandwidth is equal to 2 by f sub m. We can see that the total bandwidth is 12 kilohertz, which means the maximum frequency which you could hear from this particular station is 6000 hertz. If we were to draw a sketch of that particular station, we saw the carrier, we saw a wedge of frequencies for the upper sideband, and a mirrored wedge for the lower sideband. This was the frequency of the carrier. This would be the frequency of the carrier plus f sub m. We'll put a stipulation here that this is the maximum frequency. The maximum, the upper frequency that you could hear. Likewise, this is fc minus f sub m max. Up until now, we have kept our discussion of AM modulation in the frequency domain. It's useful to take a look at things in the time domain. So in the time domain, you end up with a signal that looks something like this. So if this was our original tone, which we were transmitting, on an oscilloscope, you would see it reflected across the axis like so. And then you would see the high frequency carrier inside that envelope. So we call this the modulating signal envelope, where the envelope describes the limits or the maximum amplitude of the high frequency carrier. The period of the modulating signal is from this point to this point here. So that's the period of f sub m, whereas the period of the carrier would be from this point to this point. While we're in the time domain, it's good to talk about how much modulation a carrier has. So again, we'll sketch the envelope, which is mirrored across like so, with the high frequency carrier contained within the envelope. Get all that in the time domain. And what we're looking for are 2 points. We're going to call this point here voltage min. We're going to call this point here voltage max. The percent modulation is described by the letter M is equal to the maximum voltage minus the minimum voltage, all divided by V max plus V min. Which means if we're given an AM signal in the time domain, we are looking on the envelope for a maximum voltage and a minimum voltage. And then we run those two numbers through this equation to determine the modulation percentage. Now that we have a metric to define modulation, we can look at the corner cases. So the first one is no modulation, which means the transmitter is running, but the person is not talking. So there's the case with no modulation. There's also the case with 100% modulation. For no modulation, in the time domain, it looks really simple. All that exists is the high frequency carrier. The envelope is unchanged. For 100% modulation, we have a signal that looks like this. Here, V max is equal to V min. Here, V min is equal to 0. In the frequency domain, a non-modulated carrier looks like that. It's just a spike at f of c. And a 100% modulated signal would look like this, with this being the frequency of the carrier, and this being fc plus f sub m, and fc minus f sub m. By the way, you can go over 100% modulation, but it is not recommended because it ends up distorting the signal. And from our Fourier theory discussion, we know that distortion adds harmonics. And if you start adding harmonics, you increase the bandwidth. If you increase the bandwidth of an AM signal, you are no longer playing nice, which means the bandwidth increases and you're now interfering with your neighbors. While we're on the topic of 100% modulation, you should know that power total is equal to the power in the carrier plus the power in the lower sideband plus the power in the upper sideband. And that ends up being 1 unit in the carrier plus a quarter unit in the lower sideband and a quarter unit in the upper sideband. So if this was 100 watts, you can expect quarter of that, or 25 watts to exist in the upper sideband, and 25 watts to exist in the upper sideband. This is only true when that transmitter is 100% modulated. On a related note, let us introduce the concept of a mixer and an adder. So we'll let this be a mixer, where the mixer has 2 inputs and 1 output. Let this be an adder with our sigma symbol. 2 inputs, 1 output. The mixer is non-linear, while the adder is linear. For the adder, if you put in 1 and 2, you would expect to get out 3. With a mixer, if you put 1 and 2, you can expect to get something else out. In block diagram form, our modulator ends up looking like this. We have a mixer, a local oscillator. The input to the mixer is F sub m, which is our baseband intelligence, and the local oscillator. So that's the carrier. The output of the mixer is the frequency of the carrier plus the frequency of the modulating signal, and the frequency of the carrier minus the frequency of the modulating signal. Notice that the carrier is not there. So what we need to do is we need to put an adder here. We need to inject the carrier back in. Now we have the carrier and FC plus FM and FC minus FM. In the near future, we will build such a circuit in the lab where we take a local oscillator, a mixer, and an adder to produce our AM modulator. If you're curious about the mathematics, you will recall this equation from chapter 1, where this is a way to describe a signal. It has a peak amplitude, it has a certain frequency, and it has a certain phase shift. We're not going to worry about phase shift at this point. This becomes our modulating frequency, and this is the frequency of our carrier. So you could say that this is B of t by some voltage for our modulating signal by sine 2 pi frequency of our modulating signal. Again, this is our voice. This is the intelligence, all multiplied by the carrier. So the voltage of the carrier, sine 2 pi frequency of the carrier. Should put a little t here as well. From trigonometry, sine A sine B is equal to 1/2 cosine A minus B minus cosine of A plus B. The takeaway is that we end up with a frequency of the carrier minus the frequency of the modulating signal and frequency of the carrier plus the frequency of the modulating signal. For some real fun, we could talk about this in the phasor domain. If this is the carrier, that vector is unmoving. It's fixed, forever fixed. To that, we add a vector for the upper sideband and a vector for the lower sideband. But the problem is that these vectors are no longer at the same frequency, and that's something we've not done before. So what ends up happening is that these vectors rotate relative to each other. So again, the carrier is fixed, but the upper sideband vector and the lower sideband vector rotate. So there will be times when the carrier is like so, and both vectors have added together like so, which means we are at a minimum, right? If this is the envelope, on this condition here, we're at a minimum. Sometime later, our lower sideband and our upper sideband have swung round such that they add to each other. At that point, we'll end up here in the time domain. We'll end up at our V max. Anywho, I thought you'd appreciate that. Well, we can talk about phasors with relationship to communications. The next time we meet, we're going to talk about different types of modulation, specifically upper sideband modulation and lower sideband modulation. The discussion will go something like this. In the frequency domain, we have a carrier and a wedge of what could be voice frequencies or music, if you like. We've described this as the upper sideband, and we've described this as the lower sideband. They are mirror images of each other. They both contain the same information, which implies that we don't need to transmit both of them. We could transmit the carrier and only the upper sideband, or we could transmit the upper sideband by itself, or we could transmit the lower sideband by itself. All of those are valid modulation forms, and each has certain advantages. And I think you can see the biggest advantage comes from this. We can talk about the bandwidth of this signal. If you transmit only the lower sideband or only the upper sideband, the bandwidth is very narrow. Instead of having a bandwidth equal to 2 by the modulating frequency, you now have a bandwidth that's equal to the modulating frequency, which means you can put more stations closer together. We would call it spectrum efficient.